Okay, today's date is the 28th of January 2026. The time now is redacted. The time now is 5:17 p.m. Basically, I'm in a computer room. What was doing now? Camera is there. Things are here. I'll be leaving soon, but we need to leave to take matter of permission. So now we request permission to leave to leave the world. But do try to um, find a more citizen community, new community. What else now? Um, today's video is on dimensional principality of the Muko OS boot systems. Muko OS, Informatic Kilo, both Oscar is a human rights operating system. It's a human rights operating system that preserves every pathway you go, every shape you take, and every form, like every persona you take, Uche, Eze, and Obi, every shape you take, every form you take, which is the two shapes you take, Uche and Obi, Eze and Obi, which are the heart and soul of the foundation and leadership and power. Uh, Via non-linearity, the OS priorities dimensional principality and dimensional principality and non-linearity. Non-linearity. So therefore, I've come to conclude the two things. So definitions of non-linearity. So any non-linear structure that can be computed on like an array or linked list must be non-isomorphic in the stream of polar connectivity. They called lattice integration via reflection. Reflecting it. So basically, a data structure can go through a transpose and it will to reflect, but the transpose represents an axis of reflection, like XYZ axis. The transpose of a matrix. For example, if you have the matrix in the form of XYZ, the transpose will be ZYX. This is an axis of reflection over this is an axis of reflection. So ZYX is the interest transpose of the matrix in one axis. You get the inverse axis to of the data structure. But this data structure has a reflection over lattice. So this direction, if you rotate the transpose XYZ, you have flip it, you get ZYX, which is basically a linked list. So you get XYZ row vector becoming a column vector when you rotate it. And the axis has to project orthogonally, so you have to rotate at a minus 45 degrees angle, which is kind of a reflection of the dimension. So the goal is to have a space where the system can always move, but the data structure is preserved. So it's a non-linear polar sequence, which is you should double the space and half the time, going for as computation isomorphic resources. The merit of this system uh, can a non-linear system. The system has both a polar axis, which is pi over 4, pi over 3, pi over 2, and pi over 1 or pi. But the main problem here I'm trying to address is this kind of the type and kind relationship of a system. VR half. So the orbit goes. So you got a time half sequence. So you have to try to map the data itself to some kind of isomorphic plane of quadrants that reflect a lattice of stability, such as gravity. Because gravity represents everything the system has every day. So that's the next step. So today I'm trying to demonstrate how the system, if you go to github.com /O for Oscar, B for Bravo, I for Indigo, N for November, E for Echo, S for Echo, U for Umbrella, S for Sarah, /M for Mike, M for Mike, U for Umbrella, K for Kilo, O for Oscar dash OS operating system. You will find macOS, you can run macOS. I'll show you how to run macOS, but here the boot sector, if you run make, and you can run the boot sector flag on the terminal and find the image files preserved. And okay, now I'll put my camera on. 1 second. So basically, now they're coming now. 1 second. Let's trust them. So, what else? So I got my board here, but I can take this out. Lucky for me, there's a board here. I'm going to show you guys this, but I can use this board too. But it's in So, that's a short. So this is basically the board that's here, the board. It's not my board, so it's basically better than the paper. So I'm gonna make use of it. Anyway, like always, this is a chalkboard. So this is a chalkboard. So this is good enough to write on. But I don't have the paper. I'm gonna ask for it today. I'm gonna ask for the stuff around later. But there is chalk and this round, I know. But this is Jesus. Oh Jesus. Anyway, so the goal of this today is I don't know. So there's no Jesus in my constitution, but it's fine. So I'm gonna clean this properly. But I'll just clean up. So I can back to the later. Maybe something here. There's nothing here. Anyway, so it's not a part of some. I don't know. So I'm gonna just go here. Basically, I'm just trying to go because I can't see that. I'm not allowed to see that. So they don't say to you, the kind of thing I'm saying, the song that comes to that dome is dimension refer to the act of dimension principality. So dimensions have principles that they obey, but without actually thinking about it, they do the work of via basically it's a quantum field tunnel that is shared, we all share via metaphysics. So the goal is to have every unit to you have pi to a number, you have a pi number. System has to present the dimensions and the principle in the dimension without explicitly holding it. So you have to have implicit rules to hold you. So I don't give you time to think, original time. You hold the time to think. For a system of linear equations, there's a non-polar rule that applies to it. So if I give a matrix, a complete matrix x, y, z, I use a function of scalar transformation, x, y. This is number 2, 3, 4, and the number 2, 2, 4 maps to 2, 3, and 4 times matrix of 5 and 3. So this is a vector 1 by 3 vector, and this can be also 3 by 1 vector. But if you have a conjugate model of it, so 3 by 1 vector. But if you get 2 and 5, which are numbers, let me calculate this quickly. 1 second, guys. So I got a paper here. I'm going to share this. I'm going to around. So you have a vector 2, 3, 4, and another vector 2, 3, and 4. And you have another vector 3, 4, 5. So 2 times 3 is 2 times 3 multiplied by 4 and 5. So I have to go to the transpose. So 2 times 3 is this gives you so give 2 times 3 gives you the matrix. 2 times 3 gives you the matrix 4. 2 times 4 gives you the matrix of 6. 6 in the entry of 1, and then 3 times 4. No, 2 times 5 gives you the x coordinate. 2 times 5 gives you 10. 2 times so this is the first matrix. So the first one is 2 times 4 is 6, and the second matrix is 2. 3 times 4 is 12. 2 times 5 is 15, and 4 times 4 is 16, and 4 times 5 is 20. So the matrix now 6, 10, 12, 11, and 11. If 4 times 4, 16, 16, 20. So this matrix is what I don't want to hold. So the goal is to have a linear, but this is a matrix I'm holding in memory. So it's an in-memory sequence. I want this matrix, I want this number. So this basically number here, 2 times 6, 2 times 6, 2 times 4 is 6, 2 times 4 is 6, 2 times 5 is 10, is the first set of numbers. 12, 3 times 4 is 12, 2 times 5 is 15, and then 4 times 4 is 16. This is an in-memory, something I don't want to hold. Because you're holding this in memory, this is a computer of it. So I want this really mapped out. So this is a non-linear system. I want to have a non-linear system that has this in memory already as dynamic result. So I just know I'm looking at my result. I just know I'm looking at it. I'm just using this kind of space of, I'm looking at this kind of structure already. And that's where the signal comes into place. So you get like so you can have any number like 3, like 6, modeled as a GCD of as a signal. So the number six has a signal, and that six basically has has an irrational number, which is like so you get like a negative one equals negative one equals I, and you get negative one equals I. So you get I times I. No, you get no, you get I equal to the square root of negative one. So you get the square root of I, which equals to I. You get some kind of gimbal notation that you can model this as. So I times square root of negative one is negative I one, negative I one, and this basically means that I. So if you get I, so if you get if I is even, if I is six. That means you get six, you get negative six. You get a table you can construct over this. But this sequence of this, so the answer here is 2 times 6 plus 10 is 16. 3, so basically, I'm trying to add 3, 12 plus 15 is what? 12 plus 15 is 27, and 16 plus 20, 16 plus 20 is 36. 36. So this matrix 16, 17, 36. So I already have the kind of system here. Answer here. But this answer is basically 16, 27, 36. It's basically the goal of the problem. But this is called the result. This is what you want. This is the result. But you can see that, I have the structure preserved. Because, 3 times 2 gives you the maximum division of 3. And then this x y is equal. So this x can be on the dimension of or quadrant of because you can compute of some of this going forward, but you're only just observing the result in space and time alone. You know what I'm saying? So the 16, 27, and 36 is basically the ones who hold in memory. But this is the result. So you don't want to hold the result, you want to hold the dynamic computation over the sparse lookup. And this is when I have a table that gives you this intermediary without which is as a computational step, without actually holding on. So this is dynamic movement. So this is tabulation. So I'm trying to define a tabulation of the system that gives you 2 times 6 is 12, 4. 4. What is solution in the middle? Which is like 2 times 4 is 6, and 2 times 5 is 10. 2 times 4 is 12, and 2 times 5 is 15. 4 times 4 is 16, and 4 times 5 is 20. So I'm going to give you that step. So that's what you're trying to hold into memory without actually looking up. It's not really computation you need to do. But so they said, the second problem is so to hold the problem. So I have to hold the solution or the solution. I really can look up the solution via a table that can construct this via polar rules. So the polar rules are basically a quantum tunnel. So let's start with this. So you get this kind of framework here. Invented. So this is listen, you get a boomerang. So really, you get a well? A well is basically a modulus density. A well is density, and you get the weight, which is the rope. So you got the rope, and you got the density of the system, what the rope can hold. So you get like a well. So you get a bucket. You get a rope, and you get a rope, and you get a bucket, and the rope has to hold the bucket. Problem. The rope has to hold the bucket. So it doesn't matter how much weight is on it. That's what matters because the dimensions have principles, and so you have 3 plus 3, 6 minimum division. We have via pi x squared plus y squared equals r squared, where r squared is a space motion. So you get x squared, which is pi. You try to model pi as a signal of x squared and y squared. Well, pi can be represented rationally, which is basically what negative I is doing. So you get a computational table of an even odd ratio, which is what I call it? Even odd. So even is minus I times minus I times minus I equals minus I equals I times minus I times minus I equals 1, negative 1, and negative 1 is basically I times minus I, which is I times I times minus I equals negative 1. Negative 1 is basically Yeah, yeah, I times I is minus one. You get I times I again, which I is a unit of x, y, z. But I times I is minus one I, minus one I, and you get minus one I. So the difference between I minus negative one, I being negative one, and this one, so you can access. But you get I times I get negative one I, and this one or negative I one. So you get a surge of the ratio of a system. So you can get from negative I to negative two I, based on the number. Because your table basically preserves I and negative one. So it's a lookup table for I and negative one. So I times negative one is I. Okay, so sorry. You get so how as I remember it, I forgot. I forgot. So you get negative R1 and then negative R, you get one. And you get negative one I, and you get one again, negative one, negative one. So you get I, you get I, you get negative one. We get a two-way table of negative I. So negative I times negative I is negative one, negative one, negative one. And you get I times negative I times negative one, I times I, and one. So I one. So you get one, positive one, and you get negative one. Sorry. So you get this table. So you get the table of positive one. Let me sit down first, so you can see what I'm saying. So I say here. So you get I. So you get I. So you get I. I get negative one. I get I get positive one. So usually you can compute positive one. So you can compute positive. So you get I times I is negative I. One times one I is negative I one. I get I times negative plus one positive one. So you can compute. So you do negative I one. This is basically a positive number because I is so our positive is our real numbers real and conjugate. So real basically you get I, so you get negative I. So that'll be that means you need to compute negative I, negative one times I to get one. And that would be what is this? So you have to do I. So you have to use what is not real. What is the so you get I times so you have to do I times I, which was negative one, and negative one times I times the square root of I, which will give you one. So basically, this will give you because you did half of it. So I'm saying the square root of one, I will give you one, but you get this one. I one plus one minus one times negative one is positive one, so you get plus one. So you get a table. So you get I times negative I, which is negative one. I times negative one equals so I times I. No, this is I times I equals negative one. Negative one times I equals negative one I. One I times positive one equals negative equals square root of I times positive one is square root of I square root of one square root of I times one times negative one, which will give you one because the square root was one means different, so the I. This imaginary unit is basically a square root. This is a half of I. So I square root of I times square root of I equals I, which is number. So you get I square negative one to negative one. So if I want negative six, if I want to construct a six, which is a six I, the first if I want to control this matrix of six, I'm saying. If I want to control this matrix of six, so this table here, so you can see on six. So if I want to control six, I have to have a mapping to that six. But that is in polar system, so it's not. So the mapping is in polar coordinate system. So the polar coordinate system is basically six. So if I have six, I have to have three and two. So three and two because three times so if I take the common group two, it takes number six. Six, the first x, six, and so I have to have three and two. But that three can be negative three or negative three times negative three, which will give you negative of negative is positive. So that will give you a positive six. So I can either construct three by negative six, by negative rule, which I don't have to think about. You go use inverse of six. So that would be two times four is six. So negative 3 times negative 3 is about dimension. So in the dimension of x, y, z, negative dimension is 6. It's positive. So that would be the table. This is my look table. This is my tables here. So the table will be negative 1 square root times. So basically, I can't remember what's my table. What's my table, guys? Send to you. So, uh, so I have to hold the system accountable. So I have to have that table control again. So I have negative 1, negative I, negative I, negative 1. And we get I, negative I, negative I, negative I. We get positive I, or negative I. Items, and you get I. So you get I, you get negative I. So you have four inputs. You get negative I, 1, negative I, negative 1, uh, positive I, and positive 1. And you get negative I, 1, negative 1, positive I, negative I, uh, negative I, negative I, positive I, negative 1. So I'm saying, so it's basically a system of negative I. So you get a system. So this seems to if I'm going to control negative systems, I get a positive side. You have to have a system of 3. So I can use negative 3. Negative 3 will give me negative I, negative 1, positive I, positive 1, negative I, negative 1, positive I, positive 1. So so basically, I have to control some. If I'm controlling negative 6. This is, I need to so if I want to get a negative, I have to get negative I times negative 1. That will be negative I times square root of I, which will give me I. So I have to do I times the square root of square I times, so I have to do I times the square root of I have to do I, so I have to do I times I times I will give me negative 1. And negative 1 will give me negative, so that times 3. So I have to have 3 3 negatives and negative I. So I have to do I negative I to the power of 3 to give me negative 3. So that'll be my signal. So that'll be my 3. So that'll be my 3. So that'll be negative 3. I'm going to control negative 2. So negative 2 will be negative I, oh, no, this should be I. So this should be I to the power of negative 3, and I to the power of 6, of 2, will give me I negative I to the power of 5, which will give me, so basically, you can see negative I to the power of 3, and negative I to the power of negative 3, and negative I to the power of 2 will give me negative 2. There is 2. But this is basically incorrect. This is correct, yes. So negative 3 times 2 is equals to 6. This is positive. So I could do this number 6. Now, 6 to conjure 10, I have to do 6. But this is incorrect because I believe this is incorrect, but it's positive number, it's a positive number. So this rule that applies of the even space because if it's odd, it's even. I think it's like if my odd is your even. So it's like if I because the dimension of even and odd, what is even which should be the bigger problem on the system. But if an ant wants to transcend, let's use this formula properly over e to the power of I to the power of e, where e is the growth of the system, to give you a system of connectivity. If you grow in a stable I to the power of let's try to do calculator. I, which is the square root of negative 1. So basically, number 6. So if I do I to the power of 10, 10 will give me, yes, I calculate 10 easily because 10 is 5 and 2, yeah. So I can do 5 and 2, negative 5 and negative 2. So give me positive. I can do it all the way 2. So I can do negative 5 will give me the square root of so I times I will give me 5i, negative 5i. So you have to have like a system. So if you get the table, the coding table is basically I then negative one, then you get to positive, then you get I, then negative one, then you get negative I. So you get I, then negative I, then you get one. So it alternates. It alternates between I and negative I and 1 and negative 1 in the sequence of x, y, z. So you have three axes, not two, Namdi, to get so wrong. So you have to get that correct, Namdi. So but I don't have a calculator, I don't have a physical calculator, the part, you don't need to, basically rational numbers. But you can use, if you get a lookup table will give you what gives you what. So you just have to measure that a reality and you know the answer is there. So it's a dynamic computation tabulation model you can use to verify stuff ahead of time. So you can get the number 6 just by looking at the measured signal of it, which are what you call imaginary units of the world, of the universe, which are like radio waves. So you can have a radio wave mean number 6, and that also has a shape and form it's in. The shape of a number 6, what does 6 figure like? Which 6 is basically a figure, a glyph, but that glyph is basically dynamic. The 6 can be in the form 6 units of everything. Yes, you get number 1, 2, 3, 4, 1, 2, 3, 4 here, 4 seats, but this 4 seat can be for 2 people. Or 1 people. So you have a total of 1 seat can be for 2 people. Which is that means you have a bigger seat. You very easy to which one person has 2 seats. So dimensionality is basically a principle of dimensionality, or basically principles of dimensions that we share over the space of architecture insane, over the shared space of lattice space. I say to you, yeah, so shared space over lattice is basically dimension, and we have every dimension is a slice in space and time. For example, we have 3 plus 3, that's x y z. You get minus x y z, which is opposite axis. So if you don't think about that, if you go forward, you go backwards. So that's why there's 3 plus 3. It's not because of someone. If I put my jug here, my cup here. So if I put my cup here, containing a drink, some drink, it's gonna spill. Yep, that's it. So just down here, I can go out view, opposite you, and this is see the mirror. I can go back and see this taking my cup in the opposite spectrum. No, because some in the mirror. But this mirror here, this glass here is a mirror. So I'm showing myself in the mirror. I can come and change this cup at any time, and this cup is enough for me to get the cup. But I'm gonna turn. So I get a cup and put it back down. See, and that cup is basically no, that's my reality. That's my 3D axis. X, Y, Z. This is my 4D paint. I have space to myself right now, and this space is just a computer room in the wall. But this space is basically for me to come. So if I leave this cup for 2-3 days, if I only exist in my reality, that must mean this cup will stay there forever, here and now forever, which is basically the cup of the drink. If I've not drunk the drink, right now it's empty. So if I show you again, that's what I'm saying. I don't have to make this space up. So look, if I pour the drink again, and fill it out, I have a system where I can pour this drink forever here, and this drink will basically be in this cup forever. If I don't wait for the days to take it, but I think it's tomorrow, but that's one dimension. So I can go back and forward anytime I want out of camera, and you can see me in this kind of glass mirror. But you will not be here, this will be taken. So with this drink presents something that I need, and I want later, This is food, this is drink, but it's literally Ribena and orange juice mixed together, the squash. So I can now come and take this drink. Whichever way I go, I can keep the cup, I can fill the cup, I can drink the cup. Well, I'll just go back and take it later. So if you go front, go back. So the motivation, so you get 3 plus 3 because of 3 axes of the wall, X, Y, Z, and 3 coordinate system. And you get 3 plus 3 you can see at one time, and other things you cannot see at another time, which is what the reflection is showing behind me, but you are behind the camera. So dimension predictability is basically meant to be a system of the real world of what we can observe at the space and time we observe, our local maximum and minimum. So we'll get 3 times 3 and 3 to the power of 3, which is the lowest maximum, which makes a full reality token of himself at one space at one time. No matter if it's a human being or missile, a human being or a missile or an AI system, the system of the which is equals to x squared x squared plus y squared equals r squared, where r is where r is radius for the space, and the space is basically a half of the full reality via lived reality spaces. So what I'm saying to you, you have 3 to the power of 3, which is 3 times 3, which is 9. And 9 times 6. 9 times 6 is basically 9 times 6 is basically 48. No, 50. 9 times 5 is 45. 54. 9 times 6 is 9 times 5 is 9 times 5 is basically 5 times 9 is 60. 60. It goes to 9 times 5 is 60. 9 times 5 times 9 is 49. So no, 48. Let me try to calculate it. 6 times 9 is 54. Yes, 54. So 54 is 6 times 9. And 6 times 9 is basically the reality you hold maximum. But you have to have, you don't need to have, you need to have 3 plus 6 plus 9, 15. So you need 15 minimum consensus to act in a space of 54, which is area. So basically the area is basically one of the dimensions of axis. But you have to put this power of 3 axes. You only go to 3 x, y, z. Unless you use 4, which is a reality can transcend, which is 4D reality, which is a 4D. You do 4, if you have 4D, you're talking about time. You share the one situation space and time. If you do, it's not stupid. You get 3 plus 1, you get 4 more reality, which is 4. And that 4 will be sharing that space within space and time. And that's what the space we all share and the time we all share here and now. Not the future, not tomorrow, not the past, but here and now. We call it moment, the present. Forever. If there is a present, this is the future. But that's the kind of gimmicky situation of it. Thank you guys for watching this video. I will show you my diagrams here. This is about gravity well. So here we've got gravity well, but this has a bucket for a rope, and that rope is basically what the system must hold indefinitely. So it must become part of that system. Nothing in the universe likes to hold anything. What do you mean to get a system? So you get a kind of system of the Earth spinning, but this is gravity well model. But this is gravity system. You get Earth spinning on the axis, but this is spinning on one axis. This is the sun. But that system is basically undefined. Until you can observe the state of the sun. Unless you get it's a geocentric model of where the sun is at the center, where we are the center of the universe. But that's impossible. It's just very stable. So the sun has to be in the center. So that's what the Earth is around the sun. So let's be honest, let's can stabilize the field, everything else not to hold. So it still works, but let's say we're not at the center of the universe, basically. This works by basically orbit. So if you think about orbits, 2, 3 stars, a star and a moon, you're thinking about the system of linear equation or a star and moon. So I'm telling you guys, guys, let's go back to here. Thank you guys for watching this video.